I'm Wenyun Zou. I came from China in 2006, and I was a PhD student with Jim from 2006 to 2011, and I'm majorly interested in metabolic theory of ecology and the life history theory. And the title here today may be a little bit too abstract, but I hope it will get more clear at the end. So, as we know for decades, the metabolic rate scale with body mass quite well, and Brian has already mentioned a lot of them, so I won't get into it. But also we know metabolic rate is also a function of the temperature, and since this will be the only equation in my whole talk, I will give it some attention. B here is the metabolic rate, and B0 prime is the metabolic constant, which varies across the different taxonomic groups. M is the body mass, which is the M in the title, partially, and T is the body temperature, and E sub A here is the activation energy, which has been mentioned detailedly in Jordan Oki's talk this morning. And I just want to simplify what the E sub A mean here is you can sort of think it's how much the temperature will affect the metabolic rate. So the value of the E sub A represents that. And just keep that in mind, I will use that value later on. So as we see from this figure, if you correct the metabolic rate with the body mass, and then it goes very clear relationship with the reverse temperature here across within all different kinds of taxonomic group. And if we do the same thing for the temperature part, correct the temperature with the metabolic rate, and you can see in a different taxonomic group, it scales nicely with the body size. So this is a quite simple equation, and that is what we can use this equation derive and understand a lot more complex question. So what we did together is we derived a growth model, general growth model, use this equation to present the general growth pattern across all the species. And if you are interested in endosome, which the body temperature doesn't affect too much by the environment, then that growth model can explain most of the stuff. But when you're dealing with exosome like insects, amphibians, fishes, most people are interested on those taxonomic groups, then the environment temperature has a huge impact on their body temperature. So if we want to understand the different growth pattern across those different temperature zones, then we need to integrate the temperature term into the growth model. So based on this equation, we derived a not temperature extended growth model on the first growth model. And what I will get into is that second growth model, which integrates with temperature. And when we talk about the temperature, we only study the optimal temperature zone, which means between those two temperature range, the fitness of the organism won't change too much. And outside those two temperatures, we know the fitness changes so much, so they have a different impact. We don't consider that situation. So what happened is we know when the temperature goes high, all the chemical reaction, biochemical reaction goes up, the rate goes up. So that's what we were expecting for exosomes growth also. As the high temperature is high, this is in red, represents high temperature, blue represents the low temperature. When you have high temperature, you can see the growth rate is higher because they have a steep slope here. And the development rate is higher because they mature earlier than the cold temperature exosomes. So there are majority during the from the empiric data, we see the majority of the exosomes actually follow this pattern, which they grow faster in the hot temperature, mature early, but they end up smaller size. And people call that temperature size rule. And we know there's a majority of the exosomes follow this temperature size rule, but there are exceptions. There are a small amount of exosomes, they actually they still grow faster, mature early, because you can see the slope is deeper and they mature early, but they end up at a bigger size compared to the same species which those ones grow in the lower temperature. Now, those are the big issues for those exosomes. We observe those phenomena, but why? Why it turns out like this? So first of all, according to that simple equation we derived, and the model derived from the equation I won't present here, but if you're interested, you can look through the paper, we figured out the activation energy, which I mentioned before, that value, which will represent how much the temperature affects the rates, play a big role here. If the so consider the complex biochemistry process inside the organism into two simple groups. One is take charge for growth, another take charge for development. I know it's too much to simplify the whole process, but that's an easy thing to just picture. And then the temperature affects the growth rate. The temperature affects the growth rate change, that activation energy value. If it's different from the temperature affect the development rate, that activation energy value, then we will expect when the temperature change for those species and they grow in the lower and higher temperature will occur in a different size. So if the temperature affect growth rate greater than the temperature effect on development rate, then you will see a reverse TSR organism, which they end up become bigger in the high temperature. But if the temperature affect the development rate much greater than the growth rate, then you will expect they end up in a much smaller body size at a higher temperature. And we have data shows those values are actually proved. Our model, those different, the growth rate, the activation energy for growth rate and the development rate, they are different and they can match up as the generally used activation energy for metabolic rate. That's one nice thing. But we still didn't solve why the majority of them follow the temperature size rule, but only a small amount of them follow reverse temperature size rule, right? Then we look back to that model again, and we got excited because according to the model we derived, we actually can calculate the energy they use for the whole development stage according to different temperature, under different temperature. So we know they grow faster, they have higher metabolic rate, but they have shorter development time. So what is total energy they use? We really don't have a clue at the beginning. So what we did is we integrate the metabolic rate over the development time, and I will use those closed circle to represent the energy required for development. Impressively, we figure out for those organisms follow temperature size rule, they need less energy to develop under higher temperature. For organisms follow those reverse temperature size rule, they need more energy to develop under higher temperature, which is interesting, right? If you think about nature selection, nature generally selects those organisms that grow faster, develop faster, but they use the minimum energy, right? So that's why they prefer to those all kinds of organisms got selected out. But for certain exosomes, they may want to avoid the predator, or they want to match their seasonal foraging pattern. They want to elongate their development time, so they prefer to live in a colder environment. But if they follow this in a cold environment, they need more energy. So the nature actually selected those organisms which use less energy to develop in the colder time. And this is just a very simple case to show how the metabolic theory of ecology, from that simple equation, we can actually derive the more complicated model to solve those more complicated questions. And as I showed, the temperature affects the life space. We already know it's going faster, but now we can quantify how fast it goes. And from the empirical data, we know the temperature affects body size, those exosomes body size bigger and small in two directions, but we actually now know why and how much they affect. And we didn't really know about how much the energy they use for those circles, because the time, not only the metabolic rate changes, time also changes, but now we actually can quantify that, how much energy you use for each different developmental stage. And that obviously interesting not for individual level, only individual level, also population and community under the global temperature change in different regions. We can actually use those concepts to learn within or across those different scales. And that will give some insight about, a lot of insight about conservation. So as a big fan with metabolic rate, I really want to thank the M and T, because those two are really easy measure parameter compared to metabolic rate itself, right? So they give us a lot of easier way to get through the more complicated question. And as we see here, the greater M and T are, the greater the B metabolic rate is. Consequently, I figured out from my personal life, my academic growth rate, it seems also follow the same pattern. The greater M and T are, the greater the growth rate is. And among my whole academic development time, I think my greatest growth rate is in UNM, because I have a wonderful mentor, Jim, and a great team member to collaborate with in both UNM and the Santa Fe Institute. So I want to thank all of you. And at the last, I want to say thank you to both Jim and Astra. You are not only the role model for my professional life and also my personal life. Thank you.